All right, so now we're going to take a look at some of the general characteristics of organic compounds. And specifically now we'll take a look at some of the physical properties. And then we'll also try to tie in some other characteristic here at the end. So in terms of the physical properties, organic compounds generally tend, well, first of all, hydrocarbons especially, they're usually extracted from crude oil, for instance. So crude oil, petroleum, has different. It can be fractionated via some chemical processes, and you can get different fractions. So gasoline, for example, is a fraction. You can get the asphalt that they pave the roads with. That's a heavier fraction, and they have some of the lighter fractions, things like ethane, methane, and some of the liquids as well. So based on this, and based on the fact that your hydrocarbons generally, which form the basis for your organic compounds. So the hydrocarbons, as we said, are made up mostly of carbons and H's, right? The presence of these types of atoms and the presence of carbon to carbon bonds, and also we have carbon to hydrogen bonds as well. Okay, it means that your hydrocarbons tend to be what's known as non-polar. So this is important because it has implications for how these hydrocarbons and organic compounds generally are going to interact with other things. So we say hydrocarbons are non-polar compounds. Generally, okay, there are always going to be exceptions, but generally, and we can apply this to organic compounds as well. And that's the reason why here is because these types of bonds that make up your hydrocarbons, carbon-carbon bonds, carbon-hydrogen bonds, these are non-polar covalent bonds. Now, what does that actually mean? Well, in a non-polar covalent bond, like between the carbon and carbon, carbon and hydrogen, remember in a covalent bond, electrons are shared, and when they're shared equally, that results in a non-polar covalent bond. And what that means also is that um, the compounds, as a result, are going to be non-polar. Now, why that is important is because generally we compare most things, most substances to water. So compared to, because water is all around us, right? It's the universal solvent, basically. Most things dissolve in water. A couple things to know about water. So water, which is H2O, okay, if we were to draw the structure for water, you'll see that there are two H's that are linked to this oxygen in the middle. The HO bond is a single covalent bond. Oxygen tends to be slightly negative O, whereas the H's tend to be slightly positive. So what this means then is that this region here of the water molecule where the H's are is overall slightly positive, whereas the region where the oxygen is slightly negative. So you essentially have two different poles, a negative pole or negative end where the O is, and then a positive end down here where the H's are. And the reason why is because in this oxygen-hydrogen bond, okay, the electrons are not shared equally. The electrons are actually being pulled towards the O rather than the H. And as we know, electrons have a negative charge. So in essence, what's happening in water is if we were to draw like a little thing showing you where the electrons are generally found, like an electron cloud, we'll see that the electrons are found generally around the O rather than the H's, right? So that's larger around the O. That's where the electrons are found. So that's why that part of the molecule is slightly negative. That's a negative pole and a positive pole. So we see that water then is a polar molecule. Whereas in your hydrocarbons, right, because they're made up of these non-polar bonds, hydrocarbons are non-polar as a result. Now, the reason why we're establishing this is because there's a simple rule that we can look at in just in chemistry in general, but in lots of things that helps us to decide to predict the behavior of different substances. And this rule goes like this. So it says like involves like. And that's a simple, very simple three-word rule. Okay, and the way that we apply this rule is also very simple. What this means is polar substances like water will dissolve or will mix with other polar things. Okay, so the like part here is that the one substance and the other substance have to have the same polarity in order for them to mix together. So if one of these things has a different polarity, they're not going to mix. So polar substances then will not dissolve in other, will not dissolve in non-polar substances. Okay, and we can give you a very simple example of this. So if you think about, if you have a container here of just water, okay, and you added some oil to this. Okay, as you know from experience, right, the oil, this is my oil here, that's purple. The oil actually is going to form a layer on the top, right? So the oil does not mix with water, and based on this simple rule up here, we can predict then, because we know water is polar. Okay, and that's probably a very important thing that you want to remember. Water is a polar molecule, and water is probably the most important molecule in the whole planet. So because water being polar, and if oil doesn't mix with it, we can then predict that oil then has to be non-polar, right? Because the only way a substance is not going to dissolve in water is if it's non-polar. So we can predict that very easily from a very simple experiment. You've done this multiple times, most likely. If you have the same thing, let's say you have some water. So if we do this the right color here. And then instead of adding oil, let's say you added some alcohol to this, some ethanol, for example, right? What you will see is that the alcohol does mix. If you stir it up, they'll mix. You won't be able to tell the alcohol from the water. So the alcohol mixes easily with the water. So then we can predict, we can conclude, not predict, we can conclude in each of these cases. Okay, we can conclude then the polarity of the ethanol or the alcohol. We can say that the alcohol is polar because it mixes with a polar substance like water. So it's a very simple, very, very simple rule, like dissolves like, but it's applicable across a whole host of situations, right? So we can use oil as our prototypical hydrocarbon in this example. So as a result, then, using oil as sort of, because oil is a hydrocarbon, we can say generally your hydrocarbons are going to be non-polar, especially when you compare it to water. Now, the other thing that we can see or you observe from this example up here is that your hydrocarbons tend to float. Your hydrocarbons, these are non-polar. And based on a simple observation, they tend to float on water as well. And we can also now predict, we can conclude then that in terms of density, that the hydrocarbons tend to be less dense than water, right? So they float on the top. So whatever is less dense is always going to float at the top. And the more dense or the denser thing is going to sink to the bottom. In this case, the water is going to be the bottom layer because it's denser than typically your hydrocarbons are going to be. So those are a couple important characteristics of the hydrocarbons and organic compounds generally. So non-polar, they tend to be less dense than water. So for example, we know that the density of H2O is 1 gram per mil. So then the density of your hydrocarbon then we can predict has to be less than 1 gram per mil, right? It doesn't matter what it is, as long as it's less than one, it should float. The other characteristic of your hydrocarbons is their volatility. Okay, and we talked about volatility a little bit before. Volatility is the ability of a substance to vaporize. Okay, so if it has a high volatility, okay, that means it vaporizes very easily. And if it has a low volatility, that means it doesn't vaporize easily. Okay, so this has then implications for some of the forces that hold these molecules together. So what we're going to see with our hydrocarbons is that the hydrocarbons, especially the small ones, are very volatile, right? Meaning that they go into the vapor phase very easily. Doesn't take a lot of energy to vaporize them. And what that means then is that the forces that hold the particles or the molecules together are very weak. And molecules close to each other are very weak. So it's very easy to break those forces of attraction between the hydrocarbons. So they vaporize, you go into the gas state a lot easier than other types of compounds, right? So compared to, and again, we're using water as our example. Okay, water is much less volatile than these small hydrocarbons. Okay, and what this means then is that the forces that hold water molecules together are much stronger. So that's a very simple thing that we can reason based on the volatility. We're not going to get too much into the types of forces or what they are. We just need to compare them. So weak forces hold these small hydrocarbons close to each other, so they're easily broken. They go into the gas phase. Much stronger forces hold water molecules together, less volatile, so they don't go into the gas phase very easily. Now, the other thing that we'll see with the hydrocarbons is that as the hydrocarbons get larger, so as the hydrocarbons get larger, in other words, the number of carbons increases, what we're going to see is that the volatility decreases. Okay, and that's the case for most things. If you're looking at the members of the same family of organic compounds, the larger the molecule is, the less volatile it is, right? That's a general trend that you'll see all the time, not just with hydrocarbons, but with other types of molecules as well. All right, so we've seen three characteristics of our hydrocarbons. Volatility, hydrocarbons generally are more volatile, especially in comparison to water. Water is less volatile because the forces of attraction between the molecules of a hydrocarbon are very, very weak compared to the forces of attraction between water molecules. Within the hydrocarbon family itself, the larger the hydrocarbon, the less volatile it is. We also saw characteristics in terms of polarity. Okay, so your hydrocarbons tend to be non-polar things, um, and compared to water, for example, and as a result, they're not going to mix with water very well. We've also looked at density differences. So hydrocarbons tend to be less dense than water, so they're going to float on top of water.